So hello everyone, welcome back to my YouTube channel. Today we are going to start with the chapter number 2, Data and Sampling Distributions, from the book Practical Statistics for Data Scientists. You can easily find the PDF of the book on the internet, Practical Statistics for Data Scientists, 50 plus essential concepts using R and Python. So chapter 1 we have already done chapter number 1 in the previous video. You can check out the video in my channel. So today we are going to start with the chapter number 2. I have taken all the topics from the book, but I have broken down the theory into point wise format, so which will be easier for us to learn and understand rather than learning the jargons and the academic stuff. And also the examples I have taken are not from the book. These are the real world examples which are used in the industry. So these examples, we have taken the examples, the real world examples, then we are going to code and interpret their results. Okay, let's start with the chapter number 2, data and sampling distributions. The big data illusion. Having petabytes of data does not mean you query all of it at once. In real-world tech environments, running heavy SQL queries across total historical data is an enormous waste of compute resources. You use controlled sampling to prototype models, design A/B tests, and check data quality quickly. Population versus sample. In product analytics, the population is the theoretical total of every users who will ever interact with your platform. The sample is the 10,000 users which actually participating in your 14-day experiment. Your entire job is measuring the sample accurately enough to predict the population's future behavior. The binomial check reality. Textbooks spend chapters on coin flips and earns. In business, a coin flip is just a conversion rate. Every binary user action, buy don't buy, click don't click, churn retain, is a binomial process. If you can model a weighted coin flip, you can model cart abandonment. So here is the picture which can show you the difference between population and sample. So I will show you the picture. So you can see this picture. A population is a subset, a sample. So you can see in this picture, a sample is the subset of population. You can see in this picture, right? Okay. Topic number 1, random sampling and sample bias. Sample, a subset of larger data set. Population, the larger data set or idea of a data set. N, capital N is the size of population, so small n is the size of sample. Random sampling, drawing elements into a sample at random. Stratified sampling, dividing the population into strata and randomly sampling from each strata. Stratum, a homogeneous subgroup of population with common characteristics. Simple random sample, the sample that results from random sampling without stratifying the population. Bias, systematic error. Sample bias, a sample that misinterprets the population. A sample bias, a sample that misrepresents the population. The A/B testing trap, quantity versus quality. Having 10 million rows of data is useful if you have the wrong data. If you launch a new checkout flow and only test it on weekend shoppers, your results are heavily biased. You cannot extrapolate those results to weekly B2B power users in analytics. A highly representative sample of 2000 users beats a biased dataset of 2 million users every time. Simple versus stratified sampling. Simple random sampling blindly picks users, which risks ignoring minority segments. Stratified sampling forces the data into strict cohorts before selecting, ensuring your test group exactly. For example, ensuring your test group exactly has 50% iOS users and 50% Android users, or splitting evenly across free versus premium tiers. This guarantees your A/B test doesn't actually skew towards one specific demographic. Self-selection bias. Relying on App Store reviews, CSAT score, or voluntary product feedback form is highly dangerous. Users who take time to write reviews are either furious or ecstatic. This creates massive self-selection bias. If you completely ignore the silent majority of normal users, giving product managers a wrapped sense of actual user experience. So here is the example 1.1, random sampling and A/B testing trap, to understand this topic of random sampling and sample bias. Okay, so I will read out the question number 1.1. So in this example, we are looking at the scenario called A/B testing trap. Here in this business problem we are trying to solve, product leadership wants to launch a beta test for a new SaaS platform feature. The issue is that our user base is heavily skewed. 80% of our users are on the free tier, while our massive enterprise clients, the whales, who actually drive our revenue, make up only 5% of the total population. We need to answer a critical strategic question. How do we pull a sample of exactly 300 users from this beta test, ensuring that the overwhelmingly majority of free users do not completely drown our valuable feedback from our enterprise clients? To model this, we are working on a simulated dataset of 10,000 SaaS users. The data tracks two main parameters: the user's account tier, which reflect that 80% free, 15% pro and 5% enterprise split, along with their weekly login frequencies. Our target metric is the sample representation by account tier for our 300% beta group. In this simulation, we are going to look at the data in two different ways. First, we will expose the danger of simple random sampling trap, which blindly pulls a heavily biased sample. Then we look at the solution called stratified sampling, where we mathematically force and split an even split of 100 users from each tier to guarantee our enterprise users have an equal voice in the test. Okay, so let's start the writing the solution. Import pandas import pandas as pd, import numpy as np. So first we simulate 10,000 SaaS users, heavily skewed population. 80% free, 15% pro and 5% enterprise, the whales. np dot random seed 42 n users equals 10,000, tiers equals np dot random dot choice free pro enterprise. Size equals n users, p equals 0.80, 0.15, 0.05. Simulate their average weekly login frequency. Average weekly login frequency. Logins equals to np dot random dot poison lam equals 3, size equals n, size equals n users, user underscore data equals pd dot data frame, user id range 1 comma n underscore users plus 1, account tier colon tiers comma weekly logins as logins, print total population breakdown, print user data, account tier dot value counts, normalize equals true into 100 dot round 1, print backslash n. Okay, now the trap, simple random sampling, pulling 300 users blindly for the beta test, simple sample equals user underscore data dot sample n equals 300 comma random state equals 42, print simple random sampling biased towards free users, print simple sample account tier dot value counts, print \n. The solution: stratified sampling, forcing the sample to pull exactly 100 users from each tier. This guarantees enterprise users have an equal voice in the A/B test. Stratified sampling, stratified sample equals user underscore data dot group by account tier comma group keys equals false dot apply lambda x dot sample n equals 100 comma random state equal to 42. Print stratified sample actionable and balanced. Print stratified sample actionable and balanced. Print stratified sample account tier dot value counts. Name tiers is not identified at line number 10. Tiers equals to name apply is not defined. Dot apply. Okay, we have our output here. So you can see the total population breakdown uh, based on the group account tier. So 80% of the account tiers are free, 15% are pro, and enterprise accounts are 4.7%. And if we look at the simple random sample output, we have 300 users to test our new dashboard. if you look at the simple random sample output, we pulled 300 users to test our new dashboard. Because we sampled blindly, the math dictated that we got 234 free users and only 14 enterprise users. If we run our A/B test on this group, the feedback and the usage mechanism will be entirely dominated by people who do not pay us. The product team will end up redesigning the dashboard to optimize the free users, completely ignoring the complex workflows of the 14 enterprise clients in the sample. This is how product roadmaps get derailed by statistical bias. By executing a stratified sample instead, we group the users by the tiers first, then randomly select 100 users from each bucket. Now when we look at the A/B results, our enterprise clients have a statistically significant voice. We can confidently tell the C-suite that this new feature improves the workflow of our highest paying accounts, not just the massive volume of free signups. Second, topic number 2, bias versus variance in product analytics. Uh, Random error versus systematic error. In any metric like tracking delivery times or session lengths, you will see natural fluctuation. This is variance or random error. This is expected and unavoidable. Bias, however, is a systematic failure. If your warehouse scanner clocks in 5 minutes low, every single delivery time is incorrectly recorded as the 5 minutes faster than reality. This is a biased process. It skews the data violently in the one specific direction. So here is an example of, here is a scatter plot of shots from the gun with true aim, which has the normal variance. Random error, it is expected and unavoidable. And second picture is of scatter plot of shots with a gun with a biased aim. This gun has the aim which is biased towards this line, as you can see. The define the user challenge. Random selection in SaaS and logistics is incredibly difficult because defining a user is complex. If you randomly sample all the customers, you will accidentally pollute your A/B test with internal employee test accounts, automated B2B API integrations, and one-time refunded buyers. You must strictly define your accessible population before sampling. Temporal bias in traffic flows. When running live A/B tests on digital products, you cannot sample based purely on total numbers. A user logging into quick commerce app at 11:30 a.m. on Tuesday behaves radically different than a user logging in at 2 a.m. on a Sunday, likely ordering late night snacks. If your sampling process ignores these temporal flows, your conversion metrics will be highly biased. So let's move to next question. Question number 2.1, bias versus variance, and define the user challenge. Okay, so in this example, we are looking at the scenario called bias versus variance and define the user challenge. In this business problem, we are trying to solve operation, and here is the problem which we are trying to solve. Operations and product leadership wants to analyze our user engagement and on-time delivery performance, but they cannot touch the raw numbers sitting on their dashboard. Before any real analysis can begin, we must answer two critical data quality questions. First, how do we filter the noise like bots, internal test accounts, and refunded orders from our raw database to strictly define our true addressable customer base? Second, when tracking delivery times, how do we visually distinguish between natural operational variance and systematic data bias, such as a broken scanner that is systematically skewing every single record? To model this, we are working with a raw database pool of 10,000 simulated users alongside an operational sample of 50 deliveries. Our target metrics are addressable user count and delivery time accuracy. We break this simulation into two parts. In the part 1, we model a populated database where only 75% of rows actually represent active customers. In part 2, we simulate a delivery tracker where our delivery time is exactly 0, meaning perfectly on time. We will model true aim, which shows natural operational variance fluctuating about 5 minutes in either direction, and we will contrast that directly with the bias name, where we simulate a systematic hardware failure that permanently shifts the entire duration 7 minutes late. Okay, so let's start to code. Import pandas as pd, import numpy as np, import matplotlib.pyplot as plt. Number 1, the define the user challenge. Filtering the noise. Simulating a raw database pool of 10,000 users. Raw underscore data equals pd dot data frame user id range 1 to 10,001, account type np, account type np dot random dot choice, active customer, internal test, API bot, refunded. P equals 0.75, 0.05, 0.10, 0.10, comma size equals 10,000. The analytics fix. The analytics fix strictly defining the accessible population. Clean underscore population equals raw underscore data raw underscore data, account type equals active customer, print if population cleaned, cleaned print if raw database rows len raw underscore data print actual addressable users, actual addressable users curly bracket len clean underscore population backslash n simulating if actual addressable users print if actual addressable users len clean underscore population backslash n I don't know why this color is coming, why this maroon color, why this brown color is not going away. Simulating variance versus systematic bias. Replicating the true aim versus biased aim scatter plots. np dot random okay, I haven't closed this. Yeah, it's fine now. np dot random dot seed 42 n underscore deliveries equals 50 target delivery time is exactly zero on time. True aim, variance only. Deliveries naturally fluctuate. Plus minus 5 minutes around zero. True variance x equals np dot random dot normal 0 comma 5 comma n underscore deliveries. True variance y equals np dot random dot normal 0 comma 5 comma n deliveries. Hashtag biased aim, variance plus systematic bias. A broken scanner logs everything 7 minutes late. 7 minutes late. Systematic bias x equals np dot random dot normal 7 comma 5 comma n underscore deliveries shifted late or early. Shifted right by 7. Deliveries deliveries systematic bias y shifted up by 5 by 7, shifted right by 7, shifted left up by 7. Executive visualization fig comma axis equals plt dot subplots 1 comma 2 comma fig size equals 14 comma 6. Plot a true aim, normal operational variance, normal operational variance axis 0 dot scatter underscore true variance x comma true variance y comma colors equals hashtag hash 2c3e50. comma alpha equals 0.7 axis dot axh line 0 comma color equals black comma lw equals 1 comma line style equals dash dash axis 0 ahv line axes axis dot set title true aim normal operational variance centered around target. Axis 0 dot set xlim minus 15 comma 25. Set axis y limit set y lim. Let's make our next plot b biased aim systematic scanner failure systematic scanner failure axis 1 dot scatter systematic bias x comma systematic bias y comma color equals hash e7 4c3c comma alpha equals 0.7 axis 1 dot title axis 1 dot axline dot line style axis 1 dot set title biased aim systematic data failure \n shifted by broken scanner error axis 1 dot set limit plt dot tight layout plt dot show Path collection dot set got an unexpected keyword arguments colors. Line number 42 colors. Okay, we have our beautiful output here. Okay, so before we authorize marketing to announce that our delivery times are suddenly 7 minutes faster, we need to look at the scatter plot matrix. Okay, we have total population cleaned. First we have cleaned our population. We had raw database rows as 10,000. After cleaning the population, actual number of addressable users were 7,587. Okay, if you look at the true aim chart on the left, that represents healthy operational variance. The dots are scattered equally around the zero line hair cross. The dots are scattered equally around zero line crosshairs. Sometimes we are a little bit early, sometimes a little late due to traffic, but structurally the system is balanced. Now look at the biased aim chart on the right. This is what our current dashboard is showing. The entire cluster of the data points has shifted violently up to the right. In a physical supply chain, you do not instantly improve logistics by 7 minutes across the board overnight. This is not a performance improvement. This is a systematic bias. It tells me that API triggering the delivered timestamp in our warehouse scanner is firing 7 minutes prematurely. If we base our corporate strategy on this right hand chart, we are making decisions on a broken scanner, not reality. Furthermore, when setting up the A/B test to fix this, notice the first block of our code. We threw our 25% of our raw database. If we don't strictly define the user and filter our internal employee accounts and API and B2B API bots, we aren't running an A/B test on our customers. We are just paying the we are just paying for cloud computing to measure our own engineers. Okay, let's move to our next topic: size versus quality and population mean. The big data trap. Quality greater than quantity. Pulling 50 millions Putting 50 million rows into a dashboard does not make you a better analyst. It makes your pipeline slow. Massive datasets are computationally expensive to clean and often mask severe data engineering errors like broken event trackers. A ruthlessly cleaned representative sample of 50,000 users will always yield a more accurate A/B test than a polluted dataset of 5 million. The sparse data extraction. When volume actually matters, the only time you need true big data is when dealing with sparse metrics like building recommendation engines or localized search algorithms. If you are trying to predict which hyperlocal restaurant a user will search for in a specific neighborhood, that exact combination of variables is incredibly rare. You need millions of rows just to find enough historical matches to build a model. The A/B testing reality: sample versus population. Textbooks obsess over mathematical symbols. Sample mean versus population mean in business. The translation is practical. The sample mean is 4%. The sample mean is 4.2% conversion rate you achieved during 2 week A/B test. The population mean is the theoretical and is the theoretical unknown conversion rate that will actually happen when you roll out the feature to 100% of the global user base. The entire goal of product statistics is improving that your sample safely predicts the population. Let's start with our question number 3.1, the big data trap and representative sampling. In this example, we are looking at the scenario called the big data trap and representative sampling. Here is the business problem which we are trying to solve. The product leadership wants to predict the true conversion rate, but there is an ongoing debate about how to source the data. The team has the access. Okay, so let's start with the question number 3.1, the big data trap and representative sampling. In this example, we are looking at the scenario called the big data trap and representative sampling. Here is the business problem which we are trying to solve. Product leadership wants to predict the true conversion rate, but there is an ongoing debate about how to source the data. The team has access to massive historical dataset of 5 million users, but it is heavily polluted with severe engineering errors such as broken trackers and bot traffic. We must answer a critical question. Here, okay, let's start again with the example question 3.1, the big data trap and representative sampling. Here is the business problem we are trying to solve. Product leadership wants to predict the true conversion rate, but there is an ongoing debate about how to source the data. The team has access to massive historical dataset of 5 million users, but it is heavily polluted with the severe engineering errors such as broken trackers and bot traffic. We must answer a critical statistical question. Will analyzing a massive unclean dataset of 5 million rows give us more accurate prediction than running a highly controlled, strictly monitored A/B test on a clean sample of just 50,000 users? To model this, we are measuring the expected conversion rate. Our parameters are comparing the massive big data set of 5 million rows against a rigorously cleaned representative A/B test sample of 50,000 rows. In our simulation, we set the true population conversion reality to exactly 5%. We model the big data trap by flooding the 5 million rows dataset with false zeros representing 60% broken or bot traffic, which artificially drags its mean down. We then contrast this directly against 50,000 users samples of validated human traffic. This will allow us to visualize exactly how a smaller, high quality sample perfectly captures reality, while, while massive uncleaned volume completely fails. Okay, so let's start to code the solution. Import numpy as np, import pandas as pd, import pandas as pd, import matplotlib.pyplot as plt. Okay, set seed for reproducibility. np.random.seed101. Define the true population reality. Population reality. True population conversion rate equals 0.05, which is 5% conversion rate 5% true conversion. To simulate the populated simulate the polluted big data set of 5 million rows. This data contains severe engineering errors, broken trackers, logging false zeros, broken trackers, logging false zeros, big big data size equals 5 million. 60% of the data is broken or bots. Always zero. 40% is real behavior. Real traffic equals np dot random dot binomial 1 comma true population conversion rate comma int big data size. Big data size broken traffic equals np dot zeros int big data size into 0.6 polluted big data equals np dot concatenate real traffic comma broken traffic. Simulate the clean representative sample. Simulate the clean representative sample 50,000 rows. Strictly monitored 2-week A/B test with validated human traffic human traffic sample size equals 50,000 clean sample equals np dot random dot binomial 1 comma true population conversion rate, sample size. Calculate the means. Calculate the means. Polluted mean equals polluted big data dot mean into 100. Sample mean equals clean sample dot mean into 100. True mean equals true population conversion rate into 100. Print f polluted big data mean equals polluted mean dot 2f curly bracket dot 2f curly bracket percentage. Print f clean A/B test sample mean sample underscore mean dot 2f bracket percentage. Print f true population mean true mean dot 2f percentage. Visualize the big data trap. The big data trap labels equals polluted big data backslash n 5 million rows, comma clean comma clean clean A/B sample backslash n 50k rows, comma true population mean. True population mean values equals polluted mean, comma sample mean comma true mean. Colors equals hash E7 4C 3C hash 2980 B9 hash 27A E60. Fig comma AX equals PLT dot subplots fig size equals 9,6. Bars equal AX dot bar labels comma values comma color equals colors comma edge color equals black. AX dot set title the big data trap. Volume versus quality. Comma font size equals 14 comma pad equals 15 comma font weight equals bold. AX dot set y label expected conversion rate percentage comma font weight equals bold. AX dot grid axis equals y. Line style equals dash dash comma alpha equals 0.7. Add value labels on top of the bars. For bar in bars height equals bar dot get height. AX dot annotate f height dot 2f percentage comma xy equals bar dot get x plus bar dot get width upon 2 comma height. xy text equals 0, 3. Text codes equals offset points, comma HA equals center, comma VA equals bottom, font weight equals bold, plt dot tight layout plt dot show. True population conversion rate is not defined. Line number 16. True population rate is not defined. Named true population conversion rate is not defined. True population conversion rate. Alright, we have the data. So there is a massive trap in modern analytics, the assumption that pulling 50 million rows into dashboard automatically makes you a better analyst. In reality, massive datasets are computationally expensive and often mask severe data engineering errors like broken event trackers or bot traffic. Look at this chart. If we run our analysis on our entire historical big data pipeline, we get conversion rate of roughly 3.11%. But that is a complete illusion caused by dirty data. Conversely, when we look at our sample mean, the 5% conversion rate we achieved during our highly controlled rigorous clean 2-week A/B test with just 50,000 users. We see it almost perfectly matches with our true population mean. The entire goal of product statistics is proving that your small sample safely predicts the global population. A ruthlessly cleaned sample of 50,000 users will always yield a more accurate prediction than a polluted database of 5 million. The only exception to this rule is when we are dealing with sparse matrices. Like if we are building a hyperlocal recommendation engine, if we need to predict which specific restaurant a user will search for in a tiny neighborhood, we strictly need millions of rows just to find enough historical matches. But for standard A/B testing and conversion analysis, quality and control will beat sheer volume every single time. Okay, we move to our next topic, selection bias and regression to mean. Selection bias resulting from the way in which observations were selected. Data snooping, extensive hunting through data in search of something interesting. Vast search effect, bias or non-reproducibility resulting from repeated data modeling or modeling data with large numbers of predictor variables. The data snooping trap, p-hacking. It is the most common sin of product managers commit. It is the most common sin product managers commit when an A/B test fails. If the overall conversion rate didn't increase, they will ask you to slice the data by OS. then by time of the day, then by region, until you have one tiny segment. For example, iOS user in Gurgaon on Sundays, that went up. If you torture the data long enough, it will confess anything. This is a pure random chance, not a real business win. The vast search effect, the stadium coin flip. If 20,000 people flip a coin 10 times, someone will get 10 heads in a row by pure luck in digital products. If a new feature launch automatically tracks 100 different metrics, statistical probability dictates that at least 5 of those metrics will show a significant increase purely by random variance. You can define a core success metric before the test begins to avoid celebrating random noise. Time interval cherry picking, a classic form of selection bias where an analyst explicitly chooses a reporting window. Example: look at this massive growth between Tuesday and Thursday, while intentionally ignoring the massive drop that occurs on Friday. Always lock in your time horizons before pulling the data. Regression to mean, novelty effect. It is a metric if a metric hits an extreme outlier. Its next movement is almost always back to the average. In tech, this manifests as the novelty effect. When you launch a redesign, users click the new button just because they are new, causing a massive day one spike in engagement. Over the next 14 days, the behavior will naturally regress to the mean. Never call an A/B test a winner on day 3. Historical context. The phenomenon was first identified by Francis Galton in 1886, who wrote it in connection with genetic tendencies. For example, children of extremely tall men tend not to be tall as their father. Okay. The solution to the novelty effect is specifying a hypothesis, then collecting the data, following randomization, and random sampling principles ensures against bias. So here is the historical context. I hope you can see the screen. And yeah, this was the example which we were talking about by Francis Galton. In this chart, as you can see, the children of extremely tall men tend not to be tall as their father. Similarly, children of extremely short men were not to be as short as their father. Okay, the behavior will naturally regress to the mean. Okay, so let's start with our question number 4.1. To understand the concept of data snooping, novelty effects, and the population mean. In this example, we are looking at the scenario called data snooping, novelty effects, and the population mean. Here is the business problem which we are trying to solve. Product leadership sees a massive surge in user engagement immediately after launching a new UI and wants to declare the A/B test a runaway success on day 3. We must answer a critical behavioral question. Is this sudden spike in engagement a permanent true shift in user behavior, or are we just witnessing a temporary novelty effect that will rapidly regress the baseline once the shiny new feature loses its appeal? To model this, we are looking at the average engagement measured in minutes per user. Our parameters involve a 14-day A/B test tracking daily active engagement across a control group, which serves as our baseline, and a variant group testing the new UI. In our simulation, we model a scenario where control group maintains a steady, predictable engagement baseline averaging 15 minutes. For the variant group, we simulate a massive novelty spike in first 3 days, which we highlight as the danger zone. We then model a mathematical regression tail where user engagement ultimately drops and settles right back to the original baseline. This simulation visualizes exactly why ending an A/B test too early can trick a business into launching a completely useless feature. Okay, so I will start to code now. Import numpy as np, import pandas as pd, import matplotlib.pyplot as plt, matplotlib.pyplot as plt, simulate a 14-day A/B test tracking daily active engagement. np.random.seed 42 days equals np.arrange 1, 15. Control group steady predictable engagement. Steady predictable engagement. Our baseline population mean. Population mean. Control engagement equals np dot random dot normal log equals 15.0 comma scale equals 1.0 comma size equals 14. Variant group massive day 1 to 3 spike novelty effect. Then regress to the mean. Then regress to the mean. Then regress to the mean. We simulate a decreasing trend that settles back to the control baseline. Novelty spike equals np dot array 24.5 comma 22.0 comma 19.5 comma 17.0 comma 16.0 comma 16.0 comma 15.5 comma 15.2. Regression tail equals np dot random dot normal los log equals 15.0 comma scale equals 1.0 comma size equals 7. Variant engagement equals np dot concatenate novelty spike comma regression tail. assemble the data set, assemble the data frame. A/B test data equals pd dot data frame day is days, control engagement minutes, control engagement minutes as control engagement variant engagement minutes variant engagement executive visualization, proving the novelty effect, proving the novelty effect, plt dot figure fig size equals 10,6 10,6, plotting both groups, plt dot plot A/B test data, A/B test data day, comma A/B test data control engagement minutes, engagement mins, comma label equal control group baseline, comma color equals #7 F8 C8 D, comma line style equals dash dash, comma line width equals 3, comma marker as X, plt dot plot A/B test data day, comma A/B test data variant engagement minutes, variant engagement minutes, comma label equals variant group new UI, comma color equals hash 2980b9, comma line width equals 3, marker equals O. Highlighting the danger zone. Highlighting the danger zone. plt.ax vspan 1, 3, color equals hash e 74c3c, alpha equals 0.15, label equals danger zone, novelty spike. Formatting for the executive deck. plt.title AB test engagement. The novelty effect versus true population mean, font size, forget font size, plt.x label plt.x label days since feature launch, comma font weight equals bold. plt.y label average engagement minutes per user, font weight equals bold. plt.xticks days, plt.ylim 10, 26, plt.legend loc equals upper right, plt.grid axis equals y, line style equals dash dash, alpha equals 0.7. plt.tight layout plt.show. An indent does not match any outer indentation level. Positional argument follows key argument. Line number 11, size equals 14. Unexpected indent. Line number 40, days cinch. अच्छा, ओके भाई. No module name mart float lib. No days is defined. Days equals. Module numpy has no attribute arrange. np dot arrange. Okay, finally key error variant engagement rules. Line number 32, variant engagement wins. Variant engagement wins. plt.grid x is equal to y line style value error line style. Okay, finally we have the output. A/B test engagement, novelty effect versus true population mean. Versus true population mean. Okay. So if you look at this chart, calling the A/B test winner, A/B test a winner on day 3 would be a catastrophic financial mistake. The blue line represents our new UI. During the first 72 hours, the highlighted is the red danger zone, where we see a massive spike in engagement. This isn't because the product is fundamentally better. This is the novelty effect. Users are clicking the new buttons simply because they are shiny and new. By the day 7, the hype wears off. The user behavior violently regresses to the mean, settling exactly where our old baseline was. Furthermore, we cannot allow the product team to data snoop to save this launch. Digging through millions of rows to find Android users on weekends had a positive metric had a positive metric is a classic trap. When you track 100 different metrics across different across a massive dataset, pure statistical variance guarantees that a few of them will look like winners. Our goal is to not find a statistical anomaly. Our goal is to increase the population mean of our entire user base. This 14-day test proves that our new UI creates a temporary illusion of growth, but ultimately delivers zero long-term business value. We should not roll out this. We should not roll this out. We should not roll out this feature. Okay. Sampling distribution and central limit theorem. Okay, let's start with our next topic, topic number 5. Sampling distributions and central limit theorem. Sample statistic. A metric calculated on a sample of data drawn from a larger population. Data distribution. The frequency distribution of individual values in a dataset. Sampling distribution. The frequency distribution of a sample statistics over many samples or resamples. Central limit theorem. The tendency of sampling distribution to take on a normal shape as sample size increases. Standard error. The variability, standard deviation of a sample statistics over many samples, not to be confused with standard deviation, which is by itself refers to variability of individual data values. Data distribution versus sampling distribution. You may separate these two in your head. The data distribution is messy, highly skewed reality of your raw user behavior. Example, individual cart behaviors. The raw distribution is what the sampling distribution is what happens if you pull a sample of 1000 users, calculate their average and then repeat that process hundreds of times. Okay, let's start with this example. Example number 5.1. In this example, we are looking at the scenario called sampling distribution and central limit theorem. Here is the business problem we are trying to solve. Operations leadership is trying to set reliable service level agreements or SLAs for our full truckload freight clients. However, looking at the raw delivery data is terrifying. While most shipments arrive quickly, severe outliers caused by breakdowns or weather can delay trucks for weeks, creating a heavily skewed and chaotic dataset. We must answer a fundamental analytical question. How can we confidently predict average performance and set realistic client expectations when our underlying raw operational data is completely unpredictable and unnormal? To model this, our target metric is freight transit time measured in hours. Our parameters involve a simulated population of 50,000 full truckload shipments. In our simulation, we model the chaotic reality of logistics using a log normal distribution. This represents a reality where most shipments are fast, but extreme outliers pull the data far to the right. We can then visualize the central limit theorem in action by pulling 1000 individual shipments to represent our raw data. We contrast this directly against the distributor of 1000 daily averages using a sample of 5 and 1000 weekly averages using a sample size of 20. This visual proves to stakeholders that even when raw data is completely chaotic, aggregated operational averages will always form a predictable normal distribution that we can use to forecast business performance. So I will start to code this solution of this problem. Import pandas as pd, import numpy as np, import cbon as sns, import cbon as sns, import matplotlib dot pyplot as plt, simulate ftl freight transit times, the chaotic reality. np dot random dot seed 42 using a log normal distribution. So you might be wondering how a log normal distribution looks like. Log normal distribution. So here is how a log normal distribution looks like. Heavily skewed towards left, a log normal distribution. Using a log normal distribution, most shipments are fast, but outliers take weeks. Population transit times. Population transit time equals pd dot series np dot random dot log normal mean equals 3.8 comma sigma equals 0.6 comma size equals 50,000. Number 2, generate the sampling distribution. Sample 1,000 random individual shipments. Random individual shipments. Individual shipments. Raw data. Sample underscore data equals pd dot data frame transit time in hours is population transit times dot sample 5 dot mean for underscore in range of 1,000 comma type mean of n equals 5 shipments. Okay, generate the sampling distribution. Sample 1,000 random individuals. Raw data. Sample data is equal to period raw data. Population transit times. Transit time hours equals population transit times dot sample 1,000 comma random state equals 1 type equals raw data individual shipments sample 2 thousand means of n equals 5 shipments. Example, a daily average. Sample mean 0.5 equals pd dot data frame transit time hours population transit times dot sample 5 dot mean for underscore range underscore in range 1000 type mean of n equals 5 shipments. Sample 3000 means of n equals 20 shipments. Sample mean 20 equals pd dot data frame transit time hours comma sample 20 dot mean in range 1000 mean of n equals 20 shipments. Results equal pd dot concat sample underscore data comma sample mean 0.5 comma sample mean 20. Executive visualization. Third, executive visualization. Seaborn facet grid. G equals SNS dot facet grid results comma call equals type comma call wrap equals 1 comma height equals 2.5 aspect equals 3 share x equals true. G dot map plt dot hist transit time in hours comma bins equals 50 color equals hash 2c 3E50, comma edge color equals white. Formatting for stakeholder deck. Formatting for stakeholder deck. G dot set access labels transit time in hours. Transit time in hours, comma frequency. Frequency. G dot set titles call name, comma font weight equals bold. Plt dot subplots adjust top equals 0.9. G dot fig subtitle FTL logistics, the Central Limit Theorem in action. Font size equals 14. Font weight equals bold. Plt dot show. I don't know why it is not running. Yeah, we have our three individual charts. So here is the interpretation. The top chart, individual shipments. If you look at the individual FTL shipments, the data is heavily skewed. While our median is around 45 hours, median simple. Anyways, while our median is around 48 hours, we have a massive tail of delayed shipments dragging out past 150 hours. If we guarantee a 48 hours SLA on a single shipment, we will constantly fail and pay penalties. The middle chart, n equals to 5 shipments. However, when we look at our daily aggregated performance, average batching of 5 shipments, the extreme delays cancel out the extremely fast runs. The data is already starting to form a predictable bell curve. The bottom chart, n equals to 50, n equals to 20 shipments. This is where our predictive power unlocks. When we evaluate carrier performance on a weekly basis, averaging 20 shipments, the distribution tightens into a perfectly narrow bell curve, standard at around 55 standard at around 55 hours. We can mathematically guarantee to our manufacturing partners that our weekly average transit time will almost never exceed 75 hours. This allows us to optimize warehouse labor and safety stock levels with absolute statistical confidence. Okay. So we have some more topic to learn here, which is this central limit theorem, engine for A/B testing, and square root of n rule. Alright. The central limit theorem, the engine for A/B testing. This is the singly most important mathematical concept in product analytics. Real world consumer tech data is never a perfect bell curve. It is heavily right skewed by whales and the zero value users. But the central limit theorem proves that if your sample size is large enough, the means of those samples will always form a perfectly normal distribution, the bell curve. The mathematical magic is what allows you to run is to the mathematical magic is what allows you to confidently run statistical tests or conversion rates and SLAs, even when underlying raw data is chaotic. Standard deviation versus standard error. Never confuse these two in an interview. Standard deviation means the volatility of individual data points. Example, how much users A card size differs from users B. Standard error measures the accuracy of your metric. Example, how far our samples average card size is from true global average. The standard error is a single metric that sums up the variability in the sampling distribution for a statistic. The standard error can be estimated using statistic based on the standard deviation S for the sample values and sample size n. Standard error measures the accuracy of your metric. The square root of n rule. To cut your standard error in half, effectively making your A/B test twice as accurate. You don't just need twice as much as data, you need 4 times as much data. This is the exact reason why detecting a massive 10% conversion lift requires a small sample, but detecting a tiny 1% lift requires running an experiment on millions of users across platforms like Blinkit or Zepto for weeks. So we move to our next topic, confidence intervals. Confidence level. The percentage of confidence intervals constructed in the same way from the same population that are expected to contain the statistic of interest. Interval endpoints. Top and bottom of confidence interval. The point estimate trap. It is an A/B test. The point estimate trap. If an A/B test shows a new checkout UI increased average order value by 48 rupees, inexperienced analysts will report exactly 45 rupees to the product manager. This is dangerous. That rupees 45 is just a point estimate from a sample. If a product manager budgets next quarter's revenue based on the exact number and it drops to rupees 10 in the production, you will be held responsible. Business translation, best and worst case scenarios. A confidence interval translates your standard error into a literal best case and worst case business scenarios. Instead of promising rupees 45, you can report 95% confidence interval on 15 to 75. This tells leadership we are mathematically highly confident the true impact is positive, but the budget for minimum of 15, not 45. The trade-off, width versus confidence. You control the confidence level. A 99% confidence interval will be extremely wide because to be nearly 100% certain, you have to account for the extreme edge cases. A 90% confidence interval will be much tighter but carries 10% risk of being completely wrong. In Tier 1 tech, 95% is the absolute gold standard. It balances the actionable precision with the acceptable risk. The sample size lever. The only way to tighten a confidence interval without sacrificing your 95% confidence level is to increase your sample size. If your interval crosses 0, the test is statistically insignificant. You cannot launch the feature because it might literally lose money. You must either run the experiment longer to collect more data or kill the feature. So here is the next question number 6.1, the point estimate trap and business budgeting. The point business trap and business budgeting. In this example, we are looking at a scenario called the point estimate trap and business budgeting. Here is the business problem we are trying to solve. Product leadership is looking at the basic A/B test dashboard, reporting a flat 45 revenue lift per user for the new checkout flow. Thrilled by this number, they want to deploy this feature immediately. They want to deploy this feature globally immediately. We must answer a critical risk management question. Is this rupees 45 lift a guaranteed reality, or does the statistical noise of our sample mean we can actually lose money if we roll out this for entire user base? To model this, our target metric is expected revenue lift per user measured in rupees. Our parameters involve a calculated point estimate of rupee 45 and standard error margin calculated for 90%, 95% and 99% confidence levels. In our simulation, we translate abstract standard error into concrete business scenarios by plotting confidence intervals. By visualizing these intervals against a zero line, which represents our break-even threshold, we show stakeholders the exact trade-off between certainty and risk. This visual proves that while 95% gold standard confidence intervals suggest a safe profit between 15 and 75, demanding 99% certainty reveals a worst case scenario where the business could actually lose money by crossing into negative territory. So I will start coding the solution. Import matplotlib.pyplot as plt. Number 1, define the statistical outputs derived from our A/B test simulation. Point estimate equals 45. The raw rupees 45 lift reported by the basic dashboard. The raw rupees 45 lift reported by the basic dashboard. By the basic dashboard. Margins of error for different confidence level. Margin of errors for different confidence levels. Calculated using standard error and z-scores z-scores. CI 90 margin equals 15. Take 90% confidence interval. Rupees 30, rupee rupee 60. CI confidence interval 95 margin equals 30. CI 95% CI equals 15, 75. 15, 75. The tech industry standard is equal to 55, 99. Minus 10 rupees to 100 rupees. Set up the visualization. Fig, ax equal plt dot subplots fig size equals 10, 5. Plot the 99% confidence interval. The 99% confidence interval. Widest and most conservative. Ax dot error bar point estimate, comma 3 comma x error equals ci 99 margin, comma fmt equals o, comma color equals hash e74c3c, comma marker size equals 8, cap size equals 8, line width equals 3, comma label equals comma label equals 90% confidence interval, comma 99% confidence interval, minus 10 to 100, minus 10 to 100, plot the 95% confidence error, the gold standard, the gold standard dot error bar format equals to 2, estimate comma 2 comma x 95% margin, empty equals to o, color hash 27ae60, marker size 8, cap size 8, line width 5, line width 4, on 95%, confidence error 30 to 60, plot the 90% confidence interval, tightest but highest risk of being wrong, tightest but the highest risk of being wrong, estimate comma 1 ci 90, hash 2980b9, okay, then add the zero line, the break even slash profitability threshold, ax dot axv line 0 comma color equals black, comma line style equals dash dash, comma line width equals 2, label equals 0 lift break even. Number 4, executive formatting. Executive formatting ax dot set vertex 1, 2, 3. Ax dot set vertex labels 90% certainty. 90% certainty. 95% certainty. 95% certainty. 99% certainty. Comma font weight equals to bold. Equals bold. Ax dot set label. Ax dot set x label expected revenue lift per user in rupees, comma ax dot set title checkout A/B test translating standard error into business scenarios. Ax dot legend LOC equals lower left, comma B box to anchor equals 0, comma minus 0.35, comma n call equals 1. Ax dot grid axis equals x, line style equals dash dash, alpha equals 0.5, alpha equals 0.5. plt dot tight layout plt dot show. CI 99 margin is not defined. CI 99 margin. Okay. So here is our output graph. If you hand a product manager a dashboard that says a unique feature increased the average order value by 45 rupees, they are going to budget next quarter's revenue exactly on rupees 45. This is what we exactly call the point estimate trap. That number is just an estimate from a sample. If it drops, to rupees 10 in production, you the analyst will be held completely responsible. To protect the business, we have to translate our math into the best and worst case scenarios using confidence intervals. Look at the green line on the chart, the 95% confidence interval. This is the gold standard in tech. We aren't promising exactly rupees 45. We are telling leadership. We are mathematically 95% confident that our revenue lift is somewhere between 15 and 75 rupees. The actionable advice. The budget for a minimum of rupees 15, not 70, not 45. You can also see the trade-offs we make as analysts. The blue line is 90% interval. It is very tight and precise, but carries a 10% risk of being completely wrong. On the other hand, the red line is our 99% interval. To be almost certain, the range has to be so wide that it actually crosses the black zero line into the negative territory. If a 95% interval ever crosses that zero line, the test is significantly insignificant, meaning the feature could literally lose the company money. If a leadership wants to, if a leadership wants a tighter interval without sacrificing your 95% standard safety standard, we only have a one lever to pull. We have to increase the sample size by letting the experiment run for another week. Okay, we move to our next topic, topic number 7, normal distribution and Z scores. Error. The difference between a data point and a predicted or average value. Standardize. Subtract the mean and divide by standard deviation. Subtract the mean and divide by standard deviation is meant by standardization. Z score. The result of standardizing an individual data point. Standard normal. A normal distribution with mean equals to 0 and standard deviation equals to 1. QQ plot. A plot to visualize how close a sample distribution is to specific distribution. For example, normal distribution. A standard normal distribution is one in which units of x-axis are represented in terms of standard deviation, standard deviations away from mean. To compare data to a standard normal distribution, you subtract the mean and then divide by standard deviation. This is also called normalization or standardization. Note that standardization in this sense is unrelated to database record standardization. A conversion to a common format. The transformed value is termed as Z score, and the normal distribution is sometimes called Z distribution. Okay, standard normal distribution. So here is how a standard normal distribution. So here is how a standard normal distribution looks like. On the x-axis there are standard deviations away from the mean, and to compare the and the transform value is termed as Z score. Okay, the normal distribution is sometimes called Z distribution. This is also called the Z distribution. The normal myth in tech. The major mistake junior analysts make is assuming their raw user data follows a perfectly bell curve. It almost never does. Consumer data is fiercely right skewed. The normal distribution primarily applies to your sampling distributions. The normal distribution primarily applies to your sampling distributions thanks to Central Limit Theorem, not to your raw day-to-day user behavior. The 95% rule or SLA architecture. If a process is normally distributed, 65% of the data falls within one standard deviation of the mean. Okay. Roughly 95% falls within two standard deviations. This is how you set operational service level agreements. If your daily average time is 20 minutes with a standard deviation of 2 minutes, promising a 24-minute delivery mean plus 2 standard deviation mathematically guarantees a 95% of on-time success rate. Z score. The apple to orange metric. How you compare an 80,000 full truckload shipment to 150 rupees quick commerce grocery order to see which one is more unusual. You use their Z score. By subtracting the mean and dividing by the standard deviation, you standardize the data. A Z score of plus 3 means the event is 3 standard deviations above its own average. In business ops, anything with a Z score above 3 is immediately lagged, is either a system fraud or a VIP whale. QQ plots. You never just assume data is normal, you prove it. A QQ plot graphs your data against a perfect normal distribution. If your data points from a single diagonal line, it is perfectly normal. If the line curves wildly at the edges, you have the fat tails or the massive outliers, meaning a standard t-test might give you false confidence. Okay, here is an example to understand the topic of normal distribution, fat tails and the QQ plot. In this example, we are looking at a scenario called normal distributions, fat tails and QQ plot. Here is the business problem which we are trying to solve. Infrastructure and cloud engineering leadership needs to accurately model server CPU utilization to optimize cloud hosting costs and prevent unexpected crashes. However, they suspect their daily operations data is not perfectly predictable. We must answer a critical diagnostic question. Does our server load follow a standard predictable normal distribution, or are extreme edge cases like viral marketing traffic spikes and system outrages creating a fat tail distribution that breaks standard forecasting models? To model this, our target metric is cloud server CPU utilization measured as a percentage. Our parameters involved 500 total data points representing daily server load scenarios. In our simulation, we model a business as usual scenario where the daily CPU load fluctuates normally around 60%. To replicate real world chaos, we inject two types of extreme outliers into the dataset: viral marketing campaigns that push the load up to 95% and severe system outrages that drop it down to 20%. Finally, we use a QQ plot or a quantile plot to map our actual concatenated data against a theoretical perfect bell curve. This visualizes exactly how the extreme outliers deviate from a normal distribution, proving to stakeholders why standard statistical forecasting will fail to predict these infrastructure emergencies. Okay, so let's start to code. Import pandas as PD, import numpy as MP, import scipy dot stats as stats, import matplotlib dot pyplot as plt, Step 1, simulate enterprise cloud data CPU utilization. np.random.seed 42. Most days CPU load fluctuates normally around 60%. Most days CPU load fluctuates normally around 60%. Business as usual equals np dot random dot normal lock equals 60, scale equals 5, size equals 450. But occasionally viral marketing campaigns cause massive traffic spikes. Outliers. Traffic spikes equals np dot random dot normal lock equals 95, scale equals 3, size equals 25. And occasionally outrages drop the load to near zero. Outages drop the load to near zero. Outages equal np dot random dot normal lock equals 20, scale equals 5, size equal 25. Combine the data to create a fat tail distribution. Combine the data to create a fat tailed distribution. CPU utilization equals np dot concatenate business as usual business as usual traffic spikes comma outages. To executive visualization, the QQ plot fig comma ax equal plt dot subplots fig size equal 7,6 scipy dot stats dot prob plot automatically calculates the quantiles and plots the theoretical red line stats dot prob plot CPU utilization comma dist equals norm comma plot equals AX. Executive formatting. Executive formatting. AX dot set title QQ plot cloud server CPU utilization cloud server CPU utilization cloud server CPU utilization comma font size equals 14 comma font weight equals bold comma pad equals 15 AX dot set X label theoretical quantiles perfect bell curve font weight equals bold AX dot set Y label ordered CPU utilization percentage actual data comma font weight equals bold adding a subtle grid for easier stakeholder reading adding, adding a subtle grid for easier stakeholder reading stakeholder reading AX dot grid true line style equals dash dash alpha equals 0.6 plt dot tight layout plt dot show. Okay, so when we look at the curve which we have got between theoretical quantiles, perfect bell curve, and between ordered CPU utilization percentage, actual data. So this is a plot between, this is a server, this is a QQ plot of server, this is a QQ plot of cloud server CPU utilization between the perfect bell curve and the actual data. The middle, business as usual. Between the theoretical quantiles of -2 and +2, our data hugs the diagonal lines perfectly. This means the 95% of the time, our server loads are highly predictable and follow the standard statistical variance. Our baseline capacity planning is accurate. However, the top right, the black swans. However, look at the data points breaking sharply upwards at the top right of the chart. These are fat tails. If we build our auto scaling architecture based solely on the perfect bell curve, we are we will drastically underestimate the severity of viral traffic spikes. A standard model predicts a max CPU load of 75%, but the reality shows us repeated, repeatedly hitting 95% plus. We must engineer for these tails, not just for the averages. Okay, let's move to our next topic: long tail distribution and skewness. Tail. Okay, so let's start with our topic number 8: long tail distribution and skewness. Long tail distributions and skewness. Tail: the long narrow portion of a frequency distribution where relatively extreme values occur at low frequency. Skew: where one tail of the distribution is longer than the other. The normal fallacy in tech. The textbook normal distribution is perfectly symmetrical. Real consumer tech data is violently asymmetrical. Whether you are looking at the user session length, customer lifetime value, or daily API requests, the data is almost always right skewed. A massive cluster of regular values on the left, with the long drawn tail of the extreme activity extending to the right. The black swan danger, SLA failures. If you assume delivery delays follow a normal bell curve, you will calculate that a 3-hour delay is mathematically impossible, a Six Sigma event. But in real world of logistics, a sudden monsoon in Gurgaon can wipe out 40% of your active fleet, causing a massive spike in 3-hour delays. Long tail data means extreme worst scenarios can happen significantly more than textbook statistics predict. Normal in the middle. When you run this data through a QQ plot, the middle 80% of your users will look perfectly normal and predictable. The deviation happens strictly in the tails. The business takeaways. When you automate operations for middle 80% of your users, you must build dedicated heavy duty operational safety nets for the extreme tails. Example: VIP support teams for whales, automated fraud bans for bottom 1%. Why we pruned the mean? This is the exact mathematical reason why the mean is dangerous metric for business reporting. A long tail distribution will literally drag the mean upwards, creating a fake inflated number that doesn't represent the actual experience to your median user. Example question 8.1: long tail distribution and traffic volatility. In this example, we are looking at a scenario called long tail distribution and traffic volatility. Here is the business problem which we are trying to solve. Platform engineering and marketing leadership are trying to forecast daily traffic volume to ensure server stability and allocate ad spend effectively. They are currently assuming that day over day traffic changes follow a standard predictable bell curve. We must answer a critical diagnostic question: does our day-to-day platform traffic actually follow a predictable normal distribution, or is our business subject to fat tail extreme or is our business subject to fat tails, extreme viral spikes and sudden crashes that happens far more frequently than standard theoretical models predict? To model this, our target metric is day over day platform traffic volatility, measured as a percentage change. Our parameters involve 1000 simulated data points representing daily traffic fluctuations. In our simulation, we model highly volatile enterprise data using a student's t distribution with a very low degrees of freedom. The mathematical setup deliberately forces fat tails, replicating a business reality where extreme outliers occurs regularly on both ends of the spectrum. We then map these actual traffic changes against a perfectly theoretical normal distribution called a QQ plot or quantile plot. By visualizing how actual data violently pulls away from the theoretical straight line at the extremes, we prove to stakeholders that using standard bell curve forecasting will dangerously underestimate the frequency and severity of massive traffic swings. Okay, so let's start with writing the solution of this question. Import 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 pandas as pd, import numpy as np, import numpy as np, import scipy dot stats as stats, import matplotlib dot pyplot as plt, simulate long-tailed enterprise data day over day traffic changes. Np dot random dot seed 42 using a student's t distribution with low degrees of freedom. Df equals to 2. This mathematically this mathematically generates fat tails, extreme outliers on both ends, extreme outliers on both ends, far more far more frequently far more frequently than a standard normal distribution. Traffic changes equal stats dot t dot rvs df equals 2 log equals 0.01 comma scale equals 0.05 comma size equals 1000. 2. Executive visualization the QQ plot. Executive visualization the QQ plot. Fig comma ax equal plt dot subplots fig size equal 6 comma 6 6 comma 6 Generate the QQ plot to compare actual traffic changes against a perfect bell curve. Generate a QQ plot to compare the traffic changes, the actual traffic changes against a perfect bell curve. Stats dot prob plot traffic changes, comma dist equals norm, comma plot equal ax. Executive formatting. Ax dot set title QQ plot day over day platform traffic volatility, comma font size equal 14, font weight equals bold, comma pad equals 15. Ax dot set x label theoretical quantiles assuming normal distribution, comma font weight equals bold. Ax dot set y label actual ordered percentage change z score, font weight equals bold. Ax dot grid true, comma line style equals dash dash, comma alpha equals 0.6. plt dot tight layout plt dot show traffic underscore changes. Positional argument follows key argument. Scale equals. Alright. So here is our QQ plot. Day over day platform traffic volatility. It is plotted between theoretical quantiles assuming normal distribution versus actual ordered percentage z score. Okay. So when representing the QQ plot to a stakeholder, the distinct shape is the most critical takeaway. The center line, the predictable middle. Between the theoretical quantiles -3 to +3, the data points stick closely to the straight red line. This means that 95% of the normal day-to-day operations, the platform traffic behaves exactly like the standard math would predict. The left tail, the downward curve. Look at the bottom left of the chart. The data drops below the straight red line. In a business context, this means that when a negative events happen, like a system outage, the drop in traffic is significantly deeper and more severe than a normal distribution model predicted. The right tail, the upward curve. Look at the top right of the chart. The data points rise above the straight red line. This indicates that when a positive traffic spike occurs, like a product launch, it's significant, it's exponentially larger than a standard model expects. Okay, so we move to our next topic, students T distribution and T test. A small n stands for sample size. Degrees of freedom, a parameter that allows the T distribution to adjust to different sample sizes, statistics, and, and number of groups. The A/B testing workhorse. Forget the textbook history. The A/B testing workhorse. Forget the textbook history about Guinness Brewery. In modern product analytics, the T distribution is the mathematical engine behind the two sample T test. Whenever you run A/B test on a continuous metric like average order value, session length, or delivery time, you use a t-test to prove whether the difference between your control and variance groups is statistically significant. Why not the normal distribution, the uncertainty tax? If you had infinite data, you would just use the perfect normal distribution. But in reality, your A/B tests have limited sample sizes. The t-distribution is essentially a normal curve with thicker tails. Those thick tails acts as an uncertainty tax. They force your confidence intervals to be a wider to be wider when your sample size is small, preventing you from falsely declaring a winning A/B test too early. Degrees of freedom and -1. In academia, this requires a massive derivation. In business, degrees of freedom is just a mathematical penalty applied to small data sets. The smaller your sample size, the lower your degrees of freedom, the thicker the tails of your t-distribution become. Once your sample size crosses a few hundred users, the t-distribution becomes mathematically identical to the normal distribution. The execution reality. You will never make you will never plot a t-curve or look up values in the textbook table. Your job is to pass two arrays of data, control and variant, into scipy.stats.ttest_int. The algorithm handles the t-distribution under the hood. Your responsibility is interpreting the resulting p-value and explaining the revenue impact to the business. The t-distribution is actually a family of distribution resembling the normal distribution but with thicker tails. The t-distribution is widely used as a reference bias. The t-distribution is widely used as a reference basis for distribution of sample means, differences between two sample means, regression parameters, or more. So how does a t-distribution looks like? So here's how a t-distribution looks like. It is a normal distribution but with thicker tails. Okay. Red the red graph is t distribution and blue graph The blue line represents the normal distribution. Okay, here is the question number 9.1. To understand the topic of the t-test, confidence interval and financial risk. In this example, we are looking at a scenario called the t-test, confidence intervals and financial risk. Here is the business problem which we are trying to solve. Product leadership is looking at the initial A/B test results for a new one-click checkout and is thrilled to see a 45 rupees increase in average order value. They want to instantly lock in the next quarter's revenue forecast based on the exact 45 rupees lift per order. We must answer a critical statistical question. Is it financially safe to budget millions based on this exact point estimate? Or do we need to calculate the true margin of error to provide leadership with the realistic best case and worst case business scenarios? To model this, our target metric is our target metric is average order value measured in rupees. Our parameters involve a two sample A/B test with 1200 users in the control group using the standard checkout. The 1200 users in the variant group testing the new one-click checkout. In our simulation, we model the raw test data where the control group averages rupees 500 and the variant group averages rupees 545, perfectly creating the 45 rupees point estimate illusion. We then execute a two sample t-test and calculate the 95% confidence interval step by step. Finally, we visualize this uncertainty by plotting the error bar against the zero line, which represents the threshold of failure. This allows us to explicitly annotate the actionable best and worst case scenarios for the executive deck, proving why we must forecast based on the statistical range rather than a single risky number. Okay, so let's start to code. Import pandas as PD, import numpy as np, import scipy dot stats as stats, import matplotlib dot pyplot as plt, simulate A/B test data for average order value, np.random dot seed 42, step control group, standard checkout, mean AOV equals to 500, high variance, mean AOV equals rupees 500, high variance, n underscore control equals 1200, control AOV equals np dot random dot normal lock equals 500, comma scale equal 120, size equal and control. Variant group, one click checkout. Hashtag variant group, one click checkout. Mean AOV is rupees rupees 545 is rupees 545. The rupees 45 point estimate lift n underscore variant equals 1200. Variant AOV equal np dot random dot normal log equals 545 comma scale equal 125, size equal n underscore variant. Number 2, execute the two sample t-test scipy dot stats handles the heavy lifting. T underscore stat comma p underscore value equals stats dot t test underscore ind variant AOV comma control AOV equal where equal false. 3, calculate the 95% confidence interval for the difference in means. Step A, find the point estimate. Mean diff equals variant AOV mean minus control AOV dot mean. Step B, calculate the standard error for the difference. Calculate the standard error of the difference. SE underscore diff equals np dot square root variant AOV dot var d dof equals 1 n underscore variant upon n underscore variant variant plus control AOV dot var ddof equals 1 n underscore control step 3 determine degrees of freedom. Determine degrees of freedom df equal n underscore control plus n underscore variant minus 2. Step D, get the critical t value for 95% confidence interval. Get the critical t value for 95% confidence interval. T underscore crit equal stats dot t dot ppf 0.975 comma df. Step E, calculate the margin of error and the confidence interval bounds. Margin of error equal t underscore crit into sc underscore diff ci lower equal mean underscore diff minus margin of error ci upper equals diff margin plus margin of error. Ci upper, okay. Print executive A/B test results AOV print f point estimate the illusion plus rupees mean underscore diff 0.2f per order print f p value statistical significance p underscore value equals 0.5 f print f 95% confidence interval the reality plus rupees CI lower 0.2 f comma plus rupees CI upper dot 2f backslash n. Hashtag 4 executive visualization. Okay, I will directly copy paste the code here. Variant mean line number 23 minus. Okay. So before we authorize the product manager to lock in the next quarter's revenue forecast based on a rupees 45 increase per order, we need to look at the statistical reality of this A/B test. First, the good news. The p-value from our two sample t-test is drastically below 0.05. This confirms that the result is statistically significant. The new one-click checkout does, in fact, drive higher spending. And it is not just the random variance. We should launch the feature. However, we absolutely cannot budget for rupees 45. The rupees 45 is merely a point estimate. The mathematical illusion drawn from a small sample size. By applying the t distribution, we calculated the 95% confidence interval, which you can see visualized here. Because our confidence interval does not cross the red zero line, we have no risk of losing money. But our uncertainty tax dictates that the true financial impact lies somewhere between 35 rupees and 54 rupees. When you sit down with the CFO to map out the runway and operations budget, you must tell them to model the worst case scenario. Tell them we are 95% confident that the new feature will yield at least rupees 35 lift per order. Any revenue above that floor is a bonus, but the budgeting for the rupees 45 point estimate is a massive unhedged operational risk. Okay, so let's start with our topic number 10, binomial distribution conversion math. Trial, an event with a discrete outcome. Example, a coin flip. Success, the outcome of interest of trial. Binomial, yes, no, 0, 1 binary, having two outcomes. Binomial trial, a trial with two outcomes. Okay, binomial distribution, distribution of numbers of successes in X trials. The engine of product analytics. Textbook use Textbooks use coin flips and buffalo nickels. In consumer tech, a binomial trial is simply a user session with a binary outcome: click, don't click, buy, don't buy, churn, retain. The binomial distribution is the exact mathematical foundation for tracking conversion rates and click-through rates. Redefining success, the target variable. In statistical programming, A success does not necessarily mean something good. It simply means the event you are trying to measure occurred. If you are analyzing logistics bottlenecks, a failed delivery or a fraudulent transaction is coded as 1 and a perfect delivery is a 0. Forecasting revenue n into p. The mean of the binomial distribution is just your number of trials multiplied by probability of success. This is the literal formula for daily revenue forecasting. If your app gets 50,000 daily active users, your historical checkout conversion rate is 3%. Your expected daily order volume is 1500. The scale shortcut. Normal approximation. Calculating raw binomial probabilities require heavy computing power. But thanks to Central Limit Theorem, when your sample size gets massive, like running an A/B test on millions of users, the binomial distribution smoothly morphs into normal distribution. This is why analysts can use standard z-test to instantly calculate the winner of a conversion rate A/B test. So how does a binomial distribution looks like? So binomial distribution's formula is this: number of trials and number of success, p probability of success, and p n minus p. 1 minus p is the probability of failure. So let's start with our question number 10.1, the binomial distribution and revenue volatility. So in this example we are looking at a scenario called the binomial distribution and revenue volatility. Here is the business problem we are trying to solve. Finance and product leadership need to forecast daily revenue from our freemium to paid upgrade funnel. They want to establish strict alerting thresholds to distinguish between normal daily fluctuations and actual system failures. We must answer a critical forecasting question. Given our daily active user count and baseline conversion rate, what is our daily expected what is our expected daily volume of upgrades, and what exact mathematical bounds should we set to trigger automatic operational alerts? To model this, our target metric is daily updates, measured as the number of successful conversions. Our parameters involve 50,000 daily active users, which acts as daily trials, with an 3% upgrade conversion rate, representing our probability of success. In our simulation, we model 365 days of user behavior as a binomial distribution, essentially running 50,000 independent coin flips every single day. Using the normal approximation of this binomial process, we calculate the expected mean and standard deviation. This allows us to define a 95% confidence operational range, roughly plus or minus 2 standard deviations, to visually establish strict red alert and viral thresholds for our executive performance dashboards. So I will start to code the solution. Import pandas as pd, import numpy as np, import matplotlib dot pyplot as plt. Setting up the binomial parameters. Number 1, setting up the binomial parameters. np.random.seed 42 daily active users equals 50,000, conversion rate equals 0.03, 0.03. Daily active users 50,000 is n. Number of trials per day. Number of trials per day. Conversion rate is 0.03. P. Probability of success. Probability of success. Simulate 365 days of daily upgrades using binomial distribution. Simulate simulate number 2. Simulate 365 days of daily upgrades using the binomial distribution. This runs 50,000 coin flips with a 3% chance of heads for 365 days straight. For 365 days straight. Daily underscore upgrades equals np dot random dot binomial. N equals daily active users, comma p equals conversion rate, comma size equals 365. Number 3. Calculate the theoretical matrix. Calculate the theoretical matrix. Normal approximation. Expected mean equals daily active users into conversion rate. Hashtag n into p. Standard deviation of binomial distribution. Hashtag standard deviation of binomial distribution equals square root of n into p into 1 minus p. Std underscore dev equal np dot sqrt dot daily active users into conversion rate into 1 minus conversion rate. Define the 95% confidence bound, roughly plus minus 2 standard deviation. Define the 95% confidence bounds confidence bounds roughly plus minus 2 standard deviations. Lower bound equal expected mean minus 2 into standard deviation, equal expected mean minus 2 into standard deviation. Upper bound equals expected mean minus 2 plus 2 into standard deviation. Print daily revenue and conversion forecast print f expected average upgrades expected mean comma point 0 f print f daily volatility standard deviation equal plus minus std underscore dev point 0 f upgrades. Standard dev print f normal operational range 95% of days lower bound point 0 f to upper bound to upper bound point 0 f. Number 4, executive visualization, the normal approximation. Executive visualization, the normal approximation. plt dot figure fig size equal 10,6. Plot the histogram of our simulated year. Plot the histogram of our simulated year. plt dot hist daily upgrades comma bins equal 20 comma color equal bins equal 20 comma color equal hash 34495 e comma edge color equals white, comma alpha equals 0.8, alpha equals 0.8. Add the expected mean and our operational bounds. Operational bounds. PLT dot AXV line expected mean comma color equals hash F1C 40F 40F comma line style equal line style equal single dash comma line width equal 3 comma label equal F equal target equal target. PLT dot AXV line lower bound comma lower bound comma color equal hash E74C 3C comma line style equal double dash equal double dash comma line width equal 2 line width equal 2 comma red label equals red alert equal red alert. PLT X PLT AXV V line upper bound color is hash 2ECC71 viral label equals viral. Formatting for executive deck. Formatting for executive deck. PLT dot title simulated daily upgrades 1 year of binomial trials comma font size equal 14 comma font weight equals bold comma font weight equal bold. PLT dot X label number of daily upgrades successes comma font weight equals bold. PLT dot Y label frequency number of days comma font weight equals bold font weight equals bold. PLT dot legend lock equal upper right plt dot grid axis equal y, comma line style equal dash dash, comma alpha equal 0.4, plt dot tight layout tight layout plt dot show. Matplotlib. Alright, so we have our simulated daily upgrades chart. So if we just hand the VP of revenue operations the n times P forecast of 1500 daily upgrades, we are setting our engineering and marketing teams up for failure, because every single user session is an independent binomial trial. Natural mathematical variance dictates that we will rarely hit exactly 1500 upgrades. By mapping out this binomial distribution and utilizing the normal approximation, we calculated the normal deviation of our specific traffic volume, which sits at roughly around 38 upgrades. When you look at the histogram, it visualizes an entire year of simulated business. We established a 95% confidence bracket between 1424 to 1576 daily upgrades. This is our normal operational range. We need to advise to VP that if we hit 1430 upgrades today, no one should panic. The marketing campaign did not fail. The checkout pipeline is not broken. This is simply the left side of the binomial curve. Okay. We only trigger a high severity incident response if daily conversions drop below the red threshold of 1424, as that mathematically proves a systematic behavior beyond random chance. Okay. Let's move to our next topic, chi-square distribution multivariate testing. Moving beyond A/B testing, a standard t-test is perfect for comparing a control group directly against one variant. But in consumer tech, product teams often want to test multiple options at once. For example, testing three different dynamic delivery fee structures, rupees 15, 29, 39 simultaneously. You cannot just run multiple isolated t-tests without correcting your statistical confidence. You use chi-square test to evaluate all of them at the same time. Count not averages. Count not averages. While t-tests measure continuous metrics like average order value or delivery time in minutes, the chi the chi-square test strictly measures categorical counts. It is the mathematical engine behind contingency table. You use it to answer questions like, is the ratio of the user who churn versus retain significantly different depending on whether they are iOS, Android or web users? Measuring departure from expectation. In business, the null expectation means business as usual. If you launch a UI redesign, You expect the proportion of users clicking the checkout button to remain relatively stable across demographic segments. The chi-square statistic mathematically measures how aggressively your actual data departs from the baseline expectation. A massive chi-square value proves your redesign caused a structural, non-random shift in user behavior. So here is the formula of chi-square distribution. Okay, and here is the observed frequency minus expected frequency whole square upon expected frequency distribution. So here is how a chi-square distribution looks like. Okay, we will move to our question number 11.1 to understand the topic of chi-square distributions. In this example, we are looking at a scenario called chi-square distribution and multivariate categorical testing. Here is the business problem we are trying to solve. Product and engineering leadership need to understand if user retention is equal across operating systems. We must answer a critical statistical question. Is user churn independent of the platform they use, or is there a statistically significant relationship between a specific platform and account cancellation, such as a critical UI bug causing massive churn on Android? To model this, our target metric is account status proportion, specifically looking at retained versus churned users. Our metric involves 3000 simulated user accounts distributed across iOS, Android, and web platforms. In our simulation, we model multivariate categorical data where Android has an intentional UI flaw causing 25% churn rate, while iOS and web experience standard 10% and 12% churn rates respectively. We build a contingency table of observed counts and execute a chi-square test to mathematically compare our observed reality against an expected baseline, which represents what numbers would look like in all platforms were perfectly equal. Finally, we convert the cross tabulation into raw percentages to normalize the volume charts and visualize the results for executives using annotated 100% stacked bar chart. So the let's start to code. Import pandas as pd, import numpy as np, import scipy dot stats as stats, import matplotlib dot pyplot as plt. Number 1, simulate multivariate categorical data np dot random dot seed 42. Number 2, simulating the 3000 user accounts across platforms with an intention with an intentional Android flaw. Platforms equal np dot random dot choice iOS comma Android comma web. comma size equal 3000, comma p equal 0.4, comma 0.4, comma 0.2. Status is equal square brackets. And for platform, in platforms, if platform equal iOS, statuses dot append np dot random dot choice returned, comma churned, returned, comma churned. P equal 0.90, comma 0.10. Elif platform equal web, statuses dot append np dot random return, comma churn. Statuses dot append np dot random p88, comma 0.12. Else statuses dot append np dot random choice retained, comma churn 75, 0.75, comma 0.25. chum underscore data equal pd dot data frame platforms, comma status equal statuses create the contingency table. Number 2, create the contingency table. Observed counts, observed cross tab equal pd dot cross tab chum data platform chum data platform square bracket, comma chum underscore data statuses chum underscore data status print observed reality raw counts print observed cross tab print backslash n backslash n. Number 3, execute the chi-square test. The chi-square test. Chi2 underscore stat comma p value chi underscore 2 test comma p value comma dof comma expected matrix equals stats dot chi2 contingency observed cross tab observed underscore cross tab. Then we convert expected metrics back to data frame for executive viewing. Convert expected metrics back to a data frame for executive viewing. Expected df equal pd dot data frame expected matrix comma index equal observed cross tab dot index comma columns equal observed cross tabs dot column observed cross tab dot column. Observe cross tab dot columns. Print print expected baseline print expected baseline if all platforms were equal. If all platforms were equal, print expected df, print \n, print statistical diagnostic, statistical diagnostic, print f chi-square statistic departure magnitude, chi-square statistic departure magnitude is equals to chi 2 underscore stat dot 2f print f p value p underscore value dot 10f \n. Number 4, executive visualization 100% stacked bar chart. Okay, so let me directly copy paste the executive visualization part. Then annotate the bars with actual percentages for p in ax dot patches width comma height equal p dot get width plus comma p dot get width comma p dot get height x comma y equal p dot get xy. If height is greater than 5, ax dot text x plus width upon 2 comma y plus height upon 2 f height 0.1 f percentage plt dot legend title equal account status comma lock equal upper right comma b box to anchor equal 1.25 comma 1 plt dot tight layout plt dot show invalid syntax line number 62 if height greater than 5 ax dot text expected an indented block. Okay, so we have our output account status proportion by platform Q3.